In this video, we will look at, say we wanted to find the equation of a tangent line to a polar curve. How would we do that? And where we'll begin is how, basically starting with the approach of how we did a parametric equation, kind of going back to a few class periods ago. So in general, we could think about the relationship or the ratio between dy and dx, or the slope of a tangent line to the point of a curve, as the ratio of the parameterized equations dy dt over dx dt, or the formula that we use to find the slope of parametric curves before. As I said when we were talking about parametric equations, we often write them as x as a function of t, f of t, and y as a different function of t, g of t. But there was no special reason why we had to use t. We could have used theta instead. And that's exactly how we could rewrite our equations. Instead of dy dt over dx dt, we could write it as dy d theta over dx d theta. Again, the relationship between what is dy dx, what's happening to y and the slope versus the ratio of what's happening to x with respect to the parameter. But why this is helpful is because with a parametric equation, both x and y are individually functions of t as r times cosine theta. And if r is a formula, a function solved for theta, we could imagine basically parametrizing a polar equation. Polar equations can always be parametrized as r cosine theta and y equal r sine theta. And so imagine we're looking at this equation, we wanted to write a parametric equation of r equal 4 cosine theta instead. We could write this as a parametric equation by just starting with the shell of x equal r cosine theta, y equal r sine theta. And if we just plug in r, because literally the polar equation is solved for r, what we would have would be x is equal to 4 times cosine squared theta. And that would give us our x coordinate for that parametric equation. And y would be equal to r sine theta, which would be 4 cosine theta sine theta. And basically, if you were wondering how could I write these equations as parametric, it's actually very simple to do that. And this would be a parametric version of this equation of a circle, which is a little bit more complicated than it needs to be. And we could do a similar approach for any of the other ones. But all of that being said, basically in general, we could solve a polar equation turn it into a parametric form, as essentially writing it as if the equation, sorry, my iPad is, my writing is a little bit off. There we go. So r as a general function of theta is typically how a polar form is written. And since x is always equal to r cosine theta and y is equal to r sine theta, that's always the direct relationship between x, y, r, and theta in polar form. We could just plug in the f of theta for r, and what we'd have is x is always equal to f of theta cosine theta, y is equal to f of theta sine of theta. Again, assuming it could be written as a function. They don't have to be functions, and if it were not, then it would be a little bit more complicated, but still doable using essentially the same approach. And now, basically, since we know the parametric formula for the slope of a tangent line, we could just plug that in. So if we wanted to know, well, what is dy d theta, we just need to know, well, what's the derivative of the y component of our equation? Well, since it's a product of a function of theta times sine of theta, we would need the product rule, and it would be first d second plus second d first. So notice that's exactly what we have: first d second f of theta times the cosine of theta, derivative of sine, plus second d first sine times f prime. There we have it. And exactly the same for x, since x is also a product of f of theta and cosine of theta. When converted into parametric form, we could use the product rule: first d second plus second d first. And this could be simplified or rewritten using Leibniz notation instead of function notation, whichever you prefer, as dr d theta, which is just the derivative of if we're putting f prime sine theta, and this is how you'll see it in a lot of textbooks, or if you look up the formula online, whichever you prefer, but f prime times sine plus r cosine theta, and in the denominator we have f prime times cosine minus r sine theta. So anyways, we could use either form of this formula to find the slope of a tangent line. So let's say, for example, we wanted to find the slope of the cardioid 3 plus 3 cosine theta. Again, we would do it positionally. We're trying to say, well, what position are we at? Just like with a function, we use x. With a parametric equation, we use t. With a polar equation, where theta is basically tells us where we're at on the polar curve. So when pi is equal to 3 or pi is equal to 2, we graphed this in class recently. And, you know, say we wanted to look at pi over 3, we're at this point on the cardioid, which would be, you know, right about here based on our rough sketch. And, you know, we could say, okay, the slope of the tangent line should, you know, what is that slope? If we wanted to know, we could use this formula. Or say, for example, at pi over 2, it appears to have, you know, a different slope over here. So if I was to just highlight those 2 points, it looks like something about there and about there. And if we wanted to know more precisely, because again, this was a rough sketch, not perfect, just due to the fact that we were using some points to create a rough sketch of what it looks like. Anyways, let's do it. Let's do the math. So again, you know, if we want to know the slope of the tangent line, that's always dy dx. So my point is, you can't just take the derivative of this and plug in theta. That will not be what you want, because again, a tangent line is always a rectangular slope based on y and x, and doing straight lines in polar form is not simple. So a more obvious approach is just figuring out, well, what is the slope in rectangular sense, dy dx, and going from there. So if we copy down our formula, well, it's first going to be nice to know, well, what is f prime, or what is dr d theta? You know, at the end of the day, the derivative of r with respect to theta, that can be done exactly normally, because this just means, well, with respect to theta, the derivative of 3, the derivative of any constant is always 0, and the derivative of cosine theta would be negative sine theta. So we get negative 3 sine theta as our derivative. Basically, if we just do the straight derivative of our polar equation, we would get that. And we need to plug all of that stuff in here to find the rectangular slope, which is how slope always is. Because this will tell us with how the radius changes as theta changes, but that's not going to give us the slope in a y-x sort of format. So if we now plug all that in, well, dr d theta is negative 3 sine theta, and what it says is that our slope is dr d theta times sine of theta, so I need to multiply by another sine plus r cosine theta. And again, r would just be plugging in the original equation times cosine of theta. And all of that is going to be divided by dr d theta, which again we solved to be 3 sine theta times the cosine of theta, plus r times the sine of theta. Sorry, not plus, minus. I can read. But anyways, I'm just plugging, but basically, let me highlight this. I'm plugging the derivative here, and I'm plugging the original function right here. Or if you prefer this format, you know, take your function on top times cosine theta, you know, similarly. We need to plug that stuff in there. And now we have a formula dy dx based on theta. And again, that's what we want to do, because theta describes the position on a polar curve always. And so we want our derivative as a function of theta as well. And now if I want to solve the slope, this would give me the general slope anywhere on that curve. Now dy dx, and again, how I could write that is, well, if I want to evaluate that as pi over 3, I just need to plug in pi over 3 and see what I'm dealing with. So the sine of pi over 3, because pi over 3 on the unit circle is going to be a little bit larger, is the larger value root 3 over 2. Whereas cosine will be only 1/2. And technically you can see the unit circle on a polar grid as just the most interior circle. Can help you remember how to evaluate those things. But of course I could rewrite this as sine squared theta, but what I'd have is, well, sine is root 3 over 2 squared. And then I'm going to have plus 3, whoops, that parenthesis came a little bit, looks a little bit awkward. There we go. Let me fix that. And then it's going to be plus 3 cosine theta. Oh, sorry. Cosine theta is 1/2. So let me undo that. Times the cosine of theta, which is also 1/2. And then all of this will be divided by negative 3 sine theta root 3 over 2 times cosine theta 1/2 minus 3 plus 3 times 1/2 all times the sine, which is root 3 over 2. And anyways, we could do the math in terms of finally calculating what all this gives us. So let's simplify it and see what happens. So if we square this, we're going to have 3/4 times 3, which would be negative 9/4. And then in the other part, this is not 3 and 1/2, this is 3 times 1/2. So we'd have 4.5, or 3/2 plus 3 is 9/2 over 2 is actually also 9/4. And then divided by, well, it doesn't actually even matter what's on the bottom, well, assuming it's not 0. But if we look at this a little bit more closely, this is going to be negative, this is going to be negative. That's definitely not going to be 0, but something. I'm just going to write, whatever that is, it's some negative number. But at the end of the day, we have 0 divided by anything, and assuming the denominator is not 0, 0 divided by anything is always 0. Again, except for 0. 0 divided by 0 is not 0. Anyways, what we end up with is a slope of 0. And going back and looking at our curve, well, it doesn't necessarily look exactly like it's 0. But again, as I said, this was a graph that we created by hand, not necessarily going to be perfect. If we look at the graph of the cardioid in a calculator, 3 plus 3 cosine theta, and now we look at the position pi over 3, notice that there is a position where there's a vertical tangent. And again, let's say we wanted to know where's the maximum value of this cardioid, or we wanted to do optimization problems. We would want to know, where is it 0? And what we've just figured out is that, okay, that point at the very top of the cardioid is at pi over 3. That's the location where the slope is equal to 0. And similarly, we could solve, well, where are the vertical tangents? Basically solve the horizontal tangents by taking the numerator, setting that equal to 0, find the vertical tangents in the undefined positions by taking the denominator, each of those individual things, setting those to 0 and solving. Obviously, it's going to be a pretty complicated equation because it involves a lot of trig, but, can be done if we have enough patience. And similarly with pi over 2, let's say we wanted to know the slope at exactly this point, pi over 2, which was right here on the curve. It appears to be maybe it's about -1. And again, we could do it precisely by plugging pi over 2 in. I'll leave that as an exercise for you to try on your own.